Good morning, everybody. Thanks for coming to the session here. Good afternoon, good evening to people who have dialed in remotely or online. My name is Kumar Sankaran, and I'm the Vice President of Software and Solutions at Ventana Microsystems. And in addition to this, I also play the role of the Chair of Platforms within RISC-V International. So our goal there is to standardize the RISC-V definition of platforms, and we'll be coming up with platforms in 2022. But in this session, we'll talk about the enterprise software ecosystem for RISC-V itself, and what are the applications and use cases for porting of applications to RISC-V. So to start with the agenda, so we'll start with the RISC-V broader ecosystem, the software itself, the target market application software stacks for RISC-V in various application segments. The second part will be porting applications to RISC-V. So we'll take some example applications of how to download the source from upstream and then compile it for RISC-V. The third part will be distro support for RISC-V. We'll talk about the offerings from Ubuntu, SUSE, Fedora and Debian, specifically with regards to RISC-V again, and then finally throw it open to questions. So that'll be the agenda. So starting with the first richer, broader software ecosystem. So this picture shows you the overall overlay of how things look. So again, this doesn't cover every single thing that is needed for the overall ecosystem. This just considers applications that are available around Linux, right? So focusing on Linux as a primary OS, and again, the enterprise market segments, these are some of the applications that are needed for deployments. So starting with the left and then working towards the right. So in terms of development tools, there's QEMU and Spike. These are powerful simulators. We use them extensively within Ventana for modeling as well as software bring up. And so those are available in open source and supported by the community. On the compiler toolchain side, the predominant standard compilers are GCC and LLVM. Again, a lot of work going on there. We have the tools and runtimes group within RISC-V that's working to optimize it, make it more functionally complete. And those pieces are also available in open source today. Going to debuggers, there's Trace32 provided by Lauterbach. There is GDB, OpenOCD. These are JTAG-based debuggers, and those are needed for bring up as well. So in terms of bring up development tools, most of them that are needed for the enterprise ecosystem are available in some form in open source today. Moving to the middle tier, which is BIOS and OS. So here, let's start with BIOS first. So there's OpenSBI, which is for people who come from the ARM world. This is sort of equivalent to ARM trusted firmware, right? So this is the firmware that runs initially when the system comes out of power on, and then starts the rest of the BIOS. So in terms of the BIOS itself, we have U-boot, there's Core Boot, there is UEFI, which is Tiano Core. All of these are available in various forms in open source, and largely complete in terms of functionality as well. Moving to OS, lots of flavors there. Linux, which is upstream Linux, is supporting RISC-V for quite a while now. And then we have distros like Fedora, Debian, OpenSUSE, Ubuntu. All of them are complete to a large extent. We'll talk more about these shortly in some of these coming slides here. And then moving to other OSs like Android for client deployments and mobile deployments. Android was announced by Alibaba earlier this year. FreeBSD and NetBSD is available as well for embedded applications. And then again, for data center infrastructure, Yocto is pretty standard. So Yocto is supported for RISC-V as well. Build root file system builds are supported as well. Right, so that's the middle tier of things as the way things stand for the BIOS and OS flavors. And moving to the right side, which is hypervisor, middleware, runtimes. So there we have things like KVM. So KVM is a standard hypervisor. It's been around for several years for RISC-V. And our goal is to ratify it in the beginning of next year. Right, so the whole spec for the H extension will be ratified. Or once it's frozen, it'll be pulled into the Linux kernel. Right? But the patches have been there for quite a while for KVM. Docker is supported as well for RISC-V for container-based applications. Moving to runtimes like Java, OpenJDK has been there for, again, quite a while. A lot of work going on there in terms of optimization of OpenJDK and improving performance. So as we move on here in the next year or so, there'll be more powerful and performant versions of OpenJDK for Java. And lastly, this is something new that started towards the middle of this year, which is on the client side. Things like Chromium and Firefox. So these are applications that run on client machines, right, like laptops, desktops, and such. So that work is pretty new. So that was started by the community in July of this year. right? So that we expect that to be available in phases starting the middle of next year, later next year, right? So that completes the picture of client-side deployments as well. So in a nutshell, all of these are available. As you see the link there, RISC-V.org, all of these are listed there. So if you want any more detail, you can always go to the repository and take a look at what things are. Again, this just shows a subset of where things are at this point in time, applying to the enterprise side of the fence. So moving to the target market apps software stack. So how do we build applications using this infrastructure, right? That was shown in the previous slide. So this shows the various stacks that can be built today. So again, moving from bottom to up, starting with QEMU as a platform, moving up with the GCC LLVM compiler, using the OpenSBI and U-boot or UEFI as the BIOS, and then further moving up the stack, again, using Linux as a baseline OS, right? So storage-wise, there is Ceph. So we ported SPDK and DPDK for the networking and storage side. We'll talk about that a little bit more on the porting section. And then OVS as well, right, which is Open vSwitch. So for storage and networking, these apps can be built, and they are available today. So we have a GitHub where we'll post the SPDK, DPDK, OVS pieces that were ported by us. Moving to virtualization, so Linux guest OSs can be run as VMs using KVM tool on KVM as a baseline support within Linux. On the security side, OpenSSL is pretty key, and there's a lot of work going on within the community for OpenSSL, right? And then that can run things like SSH and stuff. And then moving further right side, web applications, right? LAMP, Linux, Apache, MySQL, PHP, Nginx. So Apache Server, WordPress, MediaWiki, PHP, web caching applications like Memcached, MySQL. They're provided by the standard distros, right? Ubuntu being one of them. It supports all these built in today. And then on the in-memory database side, just considered one example like Redis. It's an in-memory database, pretty powerful. So that is available with RISC-V as well. So in a nutshell, using the pieces that you saw in the previous slide, we can build all these target market application stacks today. Moving on, so let's talk about some porting examples that we did, right? So what happens when you port an application to RISC-V? So we took some of these examples, and this table shows the duration that it took to port an application. So we took the example of Open vSwitch. It was just literally a day. So I'll talk about it. What does this mean, right, when I say 1 day? So Nginx, same thing. You download the sources, compile it, run it, just 1 day. SPDK, which is Storage Performance Development Kit, little bit more time. You'll see shortly why. So this provides tools and libraries for user mode storage applications. So that took about a week. And then DPDK was even bigger because it's Data Plane Development Kit, the tools, libraries for network acceleration, approximately 2 weeks to port. Right. So what are the steps? Download, install sources. We patch the sources for target architecture, which is RISC-V, compile, and then run it on a platform, and then test and validate functionality and performance. So yeah, so let's talk about OVS. So this is a busy slide, but I'll just touch on what did it mean when we ported this OVS to RISC-V. Right, so the first thing was to download it, the sources. It's 2.15, so download it from upstream. And then also install some additional tools and libraries. Some of them are shown there, like the libfdcdev, NumaDev, SSL. And the host where this was done was an Ubuntu 5.11 host. And then once the applications, the libraries, and the source is installed, you pretty much fire the build command, boot.shell, and then configure it with DPDK, and then do a make and make install, and you're done. Right? It's that simple. Right? All you do is just download it, run it, compile it, and you're done. And then to run it, we just ran it on a QEMU emulator, which is a version 4.2.1. And again, running Linux. To run it, we just ran the OVS standard boot commands, which is OVS control, OVS VS control, OVS OF control, and then tied it to DPDK. And that was it. So what was the testing like? So what did it take to install and test? So this was the actual topology of how we tested this application. So you run OVS, you create an IP forward data path through OVS, and then there is a sender, a packet sender that runs on an Ubuntu host, and then there is a packet receiver that again runs on the same Ubuntu host. And then all we are doing is sending packets, then looping it back over OVS, and then getting it back. Right? So the black picture there, it's hard to read what's there, but that's the traffic sender, and then there's the white picture at the bottom, right, that's the receiver. Right? So all we do is send the traffic, receive the traffic on the receive side, and we're done. So, and we see 100% packet receive rate, which shows that the application is actually working. Moving to Nginx, so same story here. So Nginx was pretty much download the sources, version 1.20, using wget, and then install additional libraries, compile, make install, and we're done. That's all we had to do with Nginx, right? So that's why overall this really took a day to get it running from scratch and even running it on a QEMU environment. So moving to SPDK, as I mentioned, this took about a week, and here the story was similar with a little bit of changes, right? So here we downloaded the 21.04 sources, and then one of the things that we had to do here was to add the barrier-related specific APIs for RISC-V, right? So that was the only change we had to make here, because SPDK is a library, right, that links with your application. So and then we compiled the sources, and then pretty much ran it on QEMU again. And then the rest of the thing was pretty straightforward. So once we added the barrier APIs, we did a cross-compile and then ran it on QEMU, and then we were done. And then here is what the SPDK install and test framework was. So what we did was the QEMU runs the SPDK engine, and it exposes an NVMe-based disk to a remote node via TCP. So all we were doing is NVMe over TCP, where SPDK was accelerating the NVMe access to the user, which is the host, which is the x86 host, right? So this picture kind of shows that communication there. On the right side is the NVMe OF initiator. The left side is the actual target, and the target exposes those blue drives there, which are the SSDs, to the remote host over TCP, right? So it's NVMe or TCP, which is accelerated using SPDK. So moving on, so DPDK. So here, took a while. Again, download the sources, 20.11 sources from upstream, and a lot of code changes made here. Why? Because DPDK involves changes in the kernel, there are changes in user space, there is architecture-specific optimizations that are done in user space for DPDK, and that's the reason why a lot of code changes were needed here. So in addition to the tools and libraries that were downloaded and installed, so first thing was to add a new arch and configurations to compile for RISC-V 64, because there is none existing today with DPDK, right? So none of the distros support DPDK either. So we had to do this from pretty much scratch. And then we had to add the EAL support for the new arch, right, which is a RISC-V 64 architecture. And this was a big task, right? It took most of the time, which included things like modifying specific instructions, adding barrier instructions, swapping, IO remap changes, and then also need to add enumeration of CPU features that were supported, and then adding generic Linux code for special instructions and data types that were supported, right? So like a memcopy where x86 implemented it in a certain way, we had to make those changes for RISC-V as well. Then once those were done, then the rest of the steps were pretty straightforward and easy. And then next thing was compile it and then run it. And then the run steps are shown below there. And in terms of the actual installation and test process, pretty similar picture that we did earlier, where we did OBS. So here we were just using the DPDK L2 forward test that comes with DPDK and did a network test pretty much exactly as before. Sent the packet. So there are two bridge interfaces that are created by DPDK, and we just were passing packets or switching packets from one interface to the other. The packet sender is the one again on the black picture, and the white picture is the packet receiver, and then we were seeing 100% traffic rate across the forwarded interface, right, which was the DPDK created interface. Right, so this really showed the whole DPDK library itself being linked with user space and then working correctly. So let's move on to Ubuntu, so the distro support, right? So this is a slide that really came from Ubuntu, thanks to Canonical for doing this. So this picture shows the available packages as they are on Ubuntu 21.10 between AMD 64 architecture, which is x86, ARM 64, and RISC-V 64, right? Higher the better, meaning that it shows the equivalence of all these architectures, things running on Ubuntu. Right, so you can kind of see, if you look at the x86, AMD 64, it's about 64,000 packages. With ARM 64, it's about 62,000. And with RISC-V, it's about 59,000, right? So we are pretty much the first-class citizen when it comes to the number of packages, right? Pretty well complete. It's a full offering that Ubuntu has, right? So that's important. And this is as of the 10th of October, 2021. And as time moves on, the RISC-V offering from Ubuntu gets richer and richer, right? So this shows the current picture of where things are. It shows near equivalence in the number of packages between these different architectures. Now, talking a little bit more about Ubuntu 2110. So in terms of pre-configured use cases, there is Ubuntu Server, DNS Server, LAMP, Lubuntu, Mail, OpenSSH, PostgreSQL, Print, Samba, Ubuntu Cloud, Cloud Image. These are pre-configured use cases within Ubuntu. On the available server stacks, there's LAMP, there's LEMP, which is Nginx based. So there's Lime, Mail, Mosquito, and Tomcat. Right? These are all standard offerings that are built in within Ubuntu 2110. Moving to SUSE. So what does SUSE do for RISC-V? So SUSE's approach to RISC-V has been that they want to enable the developers who in turn build the enterprise, right? So they provide all the tools, utilities to the developers, and they in turn build the enterprise operating system. So the first step is to enable developers via OpenSUSE, right? So OpenSUSE is a free public version of the offering. And the Tumbleweed release is a rolling release, which is a part of OpenSUSE. And developers gain access to the newest kernel using Tumbleweed. And the next step is to transition to OpenSUSE Leap, which is a future version. And then Leap guarantees a regular release with guaranteed stability. And also there is a specific versions are released on a regular cadence. The next final step is the enterprise release, which is commercially supported by SUSE. And that is an enterprise-grade distribution. So the goal would be to try SUSE with enterprise-level packages via OpenSUSE Leap, and then transition to SUSE Linux Enterprise Server when ready to deploy in an environment that needs commercial support, right? So that's the three-step process here with SUSE. So it's kind of illustrated in this picture here of how things start, how things go on. So as I mentioned before, we start with Tumbleweed first. So Tumbleweed features about 8,000 packages that are largely community developed. We have rolling updates. There's also a rolling base system. And then we transition to Leap, which has over 6,000 packages, again, community developed. So this has a shared core and a very stable base system, and also features a regular cadence of updates. And then the third step is the enterprise version of SUSE, which has several thousand packages, and this, they call it SUSE Linux Enterprise. And this is, consists of enterprise-grade packages, and it's commercially supported. Right? So this is the three-stage or three-phased approach that is proposed by SUSE. Moving to Fedora and Debian. So this is stuff that I've got from the Fedora website, pretty much, the wiki site for RISC-V. And Fedora also has a pretty full offering as it concerns RISC-V. So the things there, these are all pulled out from the Fedora website. So the latest disk images are available. There's a Koji build system, packages that are built by Koji. The Linux build scripts are available in GitHub. And there is also a tracker for all issues which affect Fedora on RISC-V. So it's a pretty full offering. Again, if you guys have any questions or anything, do feel free to reach out to the respective owners, whether it's Fedora or Ubuntu or SUSE. And then lastly, on Debian on the right side. So again, information is pulled out of Debian. This is a pretty cool chart, actually. So this chart, not sure if you guys can clearly see the chart, but what it's really showing is, again, the number of packages across architectures. Right? Yeah, so higher the better here. And you can kind of see, it's difficult to maybe see. I can just tell you the thing. RISC-V is actually the gray color, which is the top line below or above the green line. So the green is PowerPC 64, and the gray line is RISC-V. So you can see it's near equivalence of RISC-V 64 with PowerPC 64. Right? So again, showing a fully complete Debian distro, which is equivalent in terms of the number of packages across these multiple architectures. Right? So that's in a nutshell, shows the completeness of Debian for RISC-V. So in a nutshell, to conclude, right, so what are we concluding here? So the message here was that the RISC-V enterprise ecosystem has the majority of the needed components for target market applications. Are we saying that this is the end? No. Are we saying that this is the beginning? No. What we're saying is majority of the pieces are there to build out any kind of software stack that people would want to run on RISC-V, right? And as time moves on here, in the next year, next 2 years, next 3 years, things will continue to improve. But the core pieces to even build a full stack is there today. Distro support for RISC-V is gaining equivalence to alternate architectures, right? As you saw the pictures, right? Largely complete. Again, as I said, is this the end of the world? No. But it's a pretty good start point of showing functional equivalence between different architectures. And then yesterday, as Callista mentioned, right, so it's the RISC-V ecosystem itself is a large ecosystem of 2,400 plus members as of yesterday. So it puts RISC-V in a very good shape for expanding into additional market segments. Right? So that's all I had from my side. So I'll stop here and open it up for questions.
Not quite yet. There we go. There we go. All right, we're already getting questions online, but let's start by giving Kumar a round of applause just to thank him for so far.
Thank you.
Yeah. We have 2 questions in the chat that we'll start with. The first says, so PostgreSQL is ported. What can you say about other databases like Mongo, Oracle, MariaDB, et cetera?
Yeah. Okay, yeah, so MariaDB is available as well. Mongo, from what I can tell, I think it's work in progress from some other distros, so that should be available in the near future. But yeah, as I mentioned, if there is any specific requirement from someone, do let the distro vendors know, do let me know, we can make it happen. So yeah, yeah, that's where things are.
Okay, thank you for that one. The other question was about JVMs. So you mentioned that we have OpenJDK ported. Has anybody done any measurements to compare JVM performance to say like x86 sort of equivalent there? How are we doing performance-wise in the JVM world?
Yeah, no, I think the performance work is ongoing and the optimization work is ongoing as well. This is a good question. The question is how well does it compare in terms of performance, right? So this will be an ongoing activity, we think. It's functionally near equivalence in functional performance and functional comparison with x86. But performance-wise, it might be trailing behind at this point in time. So performance work will be going on for the next year or two, right? As and when we get target architecture, like target boards from additional vendors, right? We have the Sci-Fi boards available today, but as and when we get additional boards from vendors, we will have to run it on that as well and then optimize performance. So that'll be an ongoing activity for the next few years, yeah.
And perhaps my favorite question that's been asked so far, how can we estimate the number of days for porting custom software to RISC-V?
Yeah. No, that's a good question. How to estimate the number of days, right? Yeah. So, yeah. No, I think this is a good question, right? So, to answer this question, it really depends on the kind of application it is, right? So, the examples that we took here, some of those applications are pure user space applications. If the plumbing is there, which it is today for RISC-V, right? The bulk of the plumbing on top of Linux. If it's a Linux, let's take the example of Linux, right? For this particular example here. If you take Linux as a use case, right? If it's just a pure user space application that doesn't have any dependency on the kernel, there is no assembly code, there is no performance or custom assembly instructions added to that application, then it's just a day, as you saw, right? The OVS and Nginx, pretty much straight out of the box, download it, run it, done. Now, let's take the other example, which we took, SPDK. Things getting touched in user space, things having custom things that in assembly, things having specific user space optimization, right, based on target architecture. Would it take a few days? Yes. A few days to a week? Yes. Right, now let's take things like, as we said, DPDK, right, touching the kernel. Things touch the kernel. There's driver impact in the kernel. Again, Linux, driver impact in the kernel, user space changes, the poll mode driver has to be modified. Again, optimization done in the kernel, several weeks. Now, there might be something else that's even lot bigger, right? That might fundamentally not even have a plumbing that's available in RISC-V, right? So that might be longer. So there is no one-size-fits-all answer, to be honest with you. So the lay of the land is like, it varies depending on the kind of application. Yeah, maybe I took too long to answer the question, but hopefully I answered the question.
No, it's the best answer you can give, right? I mean, it depends, right? Let's go to the room and see if anybody has a question they want me to re-ask for them that they haven't put in the virtual session. Yes, go ahead. Let me repeat it for the folks online. The question was, can you comment about LLVM performance development? How is LLVM coming along as a compiler?
Yeah. No, I think this is part of the tools and runtimes, and it'll be covered by Philip, I believe, in a session this afternoon. He'll add more to it, but I'll give you a high-level picture. So LLVM and GCC are sort of equal candidates when it comes to RISC-V. A functional version of LLVM has always been available for quite a while now, right? As and when the extensions are getting frozen, we are pushing these patches into LLVM the same way that we are doing with GCC. And so it's like an incremental stepwise fashion of adding support and then making it functionally complete, then adding performance benefits to LLVM, right? So it's an ongoing process, but the functional version, which is relatively complete, is available today.
Yes, a quick follow-up on that. Specifically for the V extension, are you guys working with the LLVM?
Yes, that's correct. So the question was, I think I can repeat the question. V extensions, right? Vector support, right? That's what you're asking for. Short answer, yes. So the question is regarding vector support, are we working with the LLVM community? Yes, we are. Yeah, so that is active work that's going on, yes.
Okay, I'm going to go back to the virtual session for one final question. How does SPDK and DPDK performance compare to their equivalent x86? I mean, those are performance-centric libraries. That's really the intent, right?
That's correct, yeah. So that's a good question. So the one thing that we have run SPDK is in terms of the only architectural platform we have today is the Sci-Fi platform, right? And on that one, it fares reasonably well. It's near equivalent performance as you have that you see with the, let's just say, 1 gigabit Ethernet interface, right? You would get a near equivalent performance of how DPDK benefits on or shows the benefit on x86 versus the Sci-Fi RISC-V platform, right? So it's near equivalent in terms of performance here. Okay. And the same thing for SPDK as well.
All right, let's give them a round of applause as we've run out of time. Thank you very much.
Thank you.
Well done, Kumar. Thank you.